Okay, so most of you guys are here, either online or physically here. So we'll get started here. So for um, in seat today, Molly, any Molly, all right, and then Kyler, yeah, to do the disinfecting after the class. Okay, so the two number 7 disinfecting solutions, and then the paper towels on here. Okay, just wipe off the surfaces that being touched during the classroom here. Another reminder is homework 2 is assigned online. Okay, so it's due again next Tuesday. So most of you guys start working on the homework early on the first assignment. That's good. Okay, there's only a couple of you guys wait until the last day. So from the second one assignment on, I will suggest you guys to work on the problems as early as you can. Okay, because the first ones they are relatively easier. So you might not have much trouble finishing them, but on the second one if you wait until the last day, chances are you won't have all the time to finish all the problems. Okay, so get started as early as you can. Starting from this week, we'll have lab activities. So lab 1 for this week is physical measurements and uncertainties. I ask you guys to bring on your laptop because we'll be doing pretty much all the data recording and then lab report on laptop. Okay, if you don't have a laptop, you can check with library to see if there's one available to check out. Okay, all right. So those are the 3 reminders. Also, you guys received an email yesterday, right, about the numbers of students being quarantined has increased, right? Is that right? So, so then let's do the good practice. So let's wear the mask properly. So have your nose and mouth all covered. I think we are doing a good job here in this class, okay? But just a reminder here. And then remember when you are sneeze or cough or yawning sometimes, keep your face mask on, right? That's the whole purpose, right? So if you take it off and sneeze, then there's no point of wearing one, okay? So let's do um, and then I think we have a lot of people online already. So let me just have everyone unmute for right now, or mute right now for you guys online to reduce any background noise there, okay? You can unmute yourself to ask question if you have one, okay? So that's fine now. Over there. All right, so last time we talked about we actually talked about a few physical quantities, okay? So we start with the position and displacement, okay? So position is used to describe the where an object is at a particular point, okay? And then displacement is the change of position. Now, before we talk about quantities, we need to have a reference, okay? So we can use a coordinate system for the reference. You can define your origin and the positive direction, okay? And then this could be arbitrary, as I mentioned earlier or last time. So you can pick any point to be your origin, okay? And then specify any direction to be positive direction. But the goal is to have the so stick to it once it's chosen, okay? And then for convenience, you always there's a little big practice here you want to take. As so if this is a one-dimensional motion, it's best that you choose the direction for the coordinate to be along with the movement of the object, okay? And then for two-dimensional, there are also some practice you can take, but it's a little bit complicated there. Or it could be like loose, more loose, okay? So once you have enough practice, then you should be able to figure out which one is the best for you, okay? So so physics is a science class, it takes a lot of practice, okay? All right. So delta x means change in position or displacement here. And then x, we use x naught to indicate initial position of the object and xf to be the final position of the object, okay? Oops. Let's see. I think all right, there you go. All right. And then the next two quantities we talk about, one being displacement and then the other one being, or the other one, yeah, I think the just one here being introduced here. Distance here, okay, the new here. So the distance is the magnitude of the displacement between two positions. You have two positions, then distance between them will be just the magnitude. Or say, for example, in this case, it could be like, if this passenger moves from here, initial position to the final position, then he moves 4 meters, okay? Now, distance is a scalar. We mentioned that for a scalar quantity, that means you can only just use the number with appropriate unit to describe it, okay? And otherwise, if you're a quantity, you need to describe it with the some number with appropriate unit and also with a direction, then it's a vector quantity. Okay, so displacement is a vector quantity because it has magnitude, say 4 meters, and then the change in position is towards to the left. Okay, so that indicates the direction. So 4 meters plus towards to the left. So that means that quantity is a vector quantity. Okay. Now distance and distance travel could be different if you have multiple stops during the whole trip or the whole journey if you take different paths, okay? Otherwise, if it's just one stop travel, then these two are the same, okay? Distance and distance travel, they are the same. But if you take one stop in between, then these two are different, okay? And then or more stops in between, then the two will be different, okay? We also took a look at one example last time. All right, so again, and then vector quantity is formally introduced actually in section 2 in the textbook. So for any quantity that has both magnitude and direction, then it's a vector quantity, okay? Velocity is a vector quantity. You need to give it a speed, which is a magnitude, and then also the direction of the velocity, okay? Force is also a vector. You need to specify how much force is applied and in what direction, okay? And then scalar quantity, you just need magnitude, okay? Like temperature, energy, mass, etc. Okay. All right. And we also talk about velocity and speed and time. So time is the change over which changes occur, okay? Or interval over which change occurs. So its SI units is in seconds, and change in time should be final minus initial, okay? Or elapsed time, okay? Now, for simplicity issue, we always take T0 initial starting point to be T equal to 0. So then change in time is simply equal to time, okay? Or the final time in under that assumption. We talk about speed. Speed is the distance, or the average speed is the distance traveled divided by elapsed time. Okay, so V equals to D over T, D being distance, okay? T is the time. Now, during your trip, you may have varying speed, okay? That means in the some part you might be moving faster and then some part you might be moving slower, okay? So that's the case, but average speed, you just do the overall distance divided by overall time, okay? So as I said, you might be having varying speed. So at any time instant, you might be traveling at 60 miles per hour, or you might be traveling at 30 or 40 or whatever, okay? But you could work out your average speed, okay, by doing the total distance by divided by the time it takes, okay? Another quantity, velocity. Velocity is defined as displacement divided by time elapsed. So then in that case, displacement, as we mentioned, is a vector, so then velocity should be also a vector, okay? So it's a vector quantity. It has the same SI unit as speed, okay? Because speed is the magnitude of it, of the velocity, okay? Now you can graphically represent the motion of an object, okay? Um, you can do position versus time, okay? Then from there on, you can figure out what's the velocity versus time, okay? Because from the position here, if you take any 2 points, for example, from starting point here to somewhere here in the middle, it's according to the previous picture where you're going from home to a store, okay? So then at least 2 time instance, you can figure out what's the displacement, your displacement, and then divide by time t. Okay, so it's delta x over delta t, which would indicate that would be the slope of this curve between this point and that point. Okay, so then you can have your velocity there, and then on your return trip, you can do the same thing to get the velocity here from here to here. Okay, so you can see that slope will be negative. Okay, so then your velocity is negative. All right. For your speed, it's the magnitude of your velocity. So that means you are taking absolute value of your velocity. The velocity could be positive, could be negative, but if you are taking absolute value, then it's going to be positive, okay, all the time. So speed should be just positive all the time, okay. Instantaneous velocity, okay, so at between any two time instance, you can have average velocity, right? So say from point 1 to 2 or A to B, you can have an average velocity, all right? Just connecting the 2 points doing delta x over delta t, that gives you the slope of this line. But when you are just talking about one particular time instance, for example, over here, then the velocity at that point should be the instantaneous velocity, okay? How you obtain that instantaneous velocity is you do a tangent line of the curve at that particular point, okay? And then take the slope of that line. You'll get your instantaneous velocity, okay? All right, and then similarly, this is another example of this. It's pretty much just the repetition of what we saw earlier, okay? But tells you how to get a instantaneous velocity here from the graph. Again, if you are looking at the instantaneous velocity at this particular point, then you will do a tangential line there, take the slope of that tangent line, okay? You get your instantaneous velocity at that particular time instance, okay? Today we are going to look at some new sections in this textbook, okay, in this chapter of the textbook. So the first one, we'll be looking at acceleration, okay. We talk about velocity, okay. Now, velocity is the change in it's the displacement over delta t, okay. Acceleration is how fast your velocity is changing. So you'll be doing change in velocity divided by time t, okay? So for 2 time instance, okay, so for your initial time instant and final time instant, you'll be doing final minus initial to get the change in velocity, okay? And then for time instance, you'll be doing your final time instant minus the initial time instant to get the change in time t, okay? Now you probably see that we have a little bit change of notation here, Ti indicating initial, where in the previous slides we are using T naught, okay? So these two are common use notations to indicate initial status, okay? Either T naught or Ti, they are pretty much the same, okay? They are indicating the same initial status, okay? All right. So from here, you can see for the SI unit, it should be meters over second square, okay? Because velocity has a unit of meters over second, okay? And then time has a SI unit of second, okay? So it's meters over second divided by second again. So it's meters over second square, okay? That's its SI unit, all right? Now keep in mind that because acceleration is defined as change in velocity divided by time, change in time, okay? So then velocity is a vector quantity. So then therefore oscillation should be also a vector quantity. Okay, you need a magnitude as well as a direction to specify the to describe the oscillation. Okay, so a magnitude and a direction are needed. Okay. Some common oscillations for some objects are listed here, or some phenomena are listed here. Okay, so the one you might be encountering a lot is the gravitational oscillation. Okay, oscillation of gravity on Earth, 9.81. Okay, this is the one you'll be encountering a lot, meters per second square. Okay, all right. On the moon, it's about one sixth of the one on Earth. Okay, so you might want to take a note on that one. So the term oscillation, it sounds like it's indicating the object is speeding up, right? Because it says oscillating, all right? But in physics, when you are slowing down, we also call that the object has an oscillation, okay? So, but it's just negative, okay? Negative oscillation, okay? Because you are going in the opposite direction of your velocity. So you are slowing down in that case. So the object should be also having an oscillation in physics, okay? So in this case, airplane is landing, so it slows down in the process, okay? Some people may call that process as deceleration because it slows down, okay? But keep in mind, deceleration is also an oscillation. It's just negative oscillation, okay? It's just the oscillation is opposite to the direction of the motion, okay? All right. So when an object is having oscillation, its speed changes according to the direction of the motion and the direction of the oscillation, okay? So if the oscillation and then the motion has the same direction, then the speed will go up, okay? And otherwise, if the speed and or its motion and then oscillation they are in opposite direction, both in B case and C here, then the speed will slow down, will decrease, okay? Now, on the other hand, these two are also in the same direction, so the speed will go up, okay? So different scenarios. Similarly to the instantaneous velocity, okay? So the object at different time instance, it may have different oscillation. So for a given point, a time instant, we'll call it as instantaneous oscillation, okay? So to obtain the instantaneous oscillation, you can have a velocity versus time plot, okay? So then on the curve, velocity versus time curve in this green here, for an instantaneous oscillation at any point, you can just do a tangent line at that particular point and then get the slope of it, because for the slope is theta, right? Rise over run. So in this case, if you have v versus t plot, then you are doing theta v over theta t. Okay, this is the same as the definition for your oscillation, theta v over theta t. So that means the slope from a velocity versus time plot is the oscillation. Okay. All right. So that's your instantaneous oscillation, how you can get it. Now, if you are looking for average oscillation between 2 points, say point 1 and point 2, T1 and T2 here, then you take those 2 points out of your curve, you connect them, and then work for the slope of this line. Okay, and then this will be your average. Okay, oscillation. This will give you your average oscillation. All right, and then similarly from T2 to T3, if you take those 2 points out and then connect them, solve for the slope of that straight line, it will give you average oscillation between T2 and T3. Okay. So let's have a practice here. The oscillation. So this one says a particle has oscillation of 6.24 meters per second square for 0.450 seconds. Okay, so your t is equal to 0.450 second. At the end of this time, the particle's velocity is 9.31 meters per second. What was the particle's initial velocity? All right, so the equations we learned today is average velocity, okay, or average oscillation. So this is the equation we learned today. So A average is equal to delta V over delta T, or V final minus V initial, divided by T final minus Ti, okay? So this is the 0.45 seconds, okay? And then it gives you this average oscillation, all right? It's asking you, and then also the final velocity is asking you to solve for this guy, okay? So this is delta T, all right? So give it a try on this one. And then if you have your answers, you can click on the problem here. It should direct you to where you can input your answer there, okay? All right, I think many of you guys have submitting the responses online here. Let's take a look at the solution together. So we are given that oscillation is equal to 6.24 meters per second square. Okay, we are given that the time t or delta t. All right, so either t or delta t, because we'll take initial time as t0, so then delta t is the same as t. Okay, that is 0.450 second. We know the final velocity is 9.31 meters per second. Okay, and today we learn that oscillation or average oscillation between these two time instants. Okay, you can just say A, or you can do A sub AV, is up to you. So I'm just going to use A here because that's the only oscillation we are dealing in this problem. Okay, that is equal to delta V over T or delta T. Okay, and then delta V should be equal to final minus initial. Okay, so we are connecting the quantities in this equation here. We are given A, we are given delta T, we are given V final. Then we'll be solving for V initial. Okay, so we'll be solving for V initial here. So what you want to do is multiply both sides by delta T first, right? So multiply by delta T, multiply by delta T to get rid of delta T on the right. So A times delta T equals to V final minus V initial. Okay. Now for V initial here, you can so if you are very familiar with algebra, I think you can figure out this easier. V initial should be equal to V final minus A times delta T. All right. So if not, then you can do a couple more steps. You can subtracting both sides by V final. Okay. Then get rid of V final on the right hand side. So then A times delta T minus V final will be equal to your minus your VI, right? So to get rid of the minus, you multiply both sides by -1, okay? -1. So then it will give you V final minus A times delta T, all right? Now we can plug in the numbers because we know everything here on the right-hand side. We're looking for VI on the left here, okay? So 9.31 meters per second minus 6.24 meters per second square times 0.450 second, okay? So the second here will cancel out 1 second down here. Then this is meters per second remaining, okay? The same as this one. So your final answer should be in meters per second. You plug in everything into your calculator. 9.31 minus 6.24 times 0.45 will give you 6.50. I think 6.502 meters per second, but we only need 3 digits here because everything is given in six figures or 3 digits, okay? So then you don't need the 2 there, okay? So 6.50 meters per second as your initial velocity on this one, okay? Questions you guys might have? And for you guys online, you have to unmute yourself to ask question, okay? So if you have question, unmute yourself, okay? All right, so this is on the first example here. Now let me share back the screen here. So for the responses I got, yeah. So you guys have 6.50. That should be the correct answer, okay? And then when you are doing homework, 6.5 should be also acceptable by expert TA, okay? Or this one, all right? But if you get different numbers, a few of you guys did that, okay? Check on with solution to see where you get it wrong, okay? Again, for expert here, it doesn't care about sig figs, okay? So whatever your calculator says, you can just put the numbers from your calculators on the system, okay? All right. So let's have a quick review on what we have learned so far in this chapter, okay? So the first thing we learned is distance, or some of the key quantities. I would like to have a quick review here. So the distance is the total length of the travel between 2 points, okay? So it should be always greater than 0 because it's the magnitude of the displacement, okay? So it should be always greater than 0. It's a scalar quantity. You don't need a direction to specify it, okay? And put this up for online folks. For displacement, it's a vector quantity, okay? It's change in position. That means final position minus initial position, okay? So you need a magnitude and then direction for it. Average speed is distance divided by time elapsed. So it's a scalar quantity because distance is scalar. Scalar over a scalar is still a scalar, all right? Velocity is change in displacement over time t. So displacement is a vector quantity. So divided by a scalar, it's a vector. For acceleration, it's change in velocity divided by time t. Okay, change in time t. So velocity is a vector quantity. So then acceleration is also a vector quantity. Okay. All right. And then I think the equations we learned so far. Okay, so this equation here or here and here. So pretty much those 4 equations here. That's what we learned so far in the textbook in this chapter. Okay. So next we'll be looking at those definitions and then the equations associated with the definition, and then we'll be doing some algebra about those equations to get some a list of equations that we will be utilizing so often in this class. Okay. So first, let's do a little bit of cleaning up here on notations. Okay. So we are going to just use the t instead of delta t, okay, when we are playing around with this equation. So we have less handwriting to do here, okay, we get rid of delta t, the delta before the t. So delta x is equal to x minus x naught, okay, so x naught means x0, so we are dropping the final, okay, sub f here, x sub f here, so x then is the final position, v is the final velocity, okay. So get rid of 1 letter there for each of the terms. For acceleration, in this chapter, we'll be just doing constant acceleration. That means acceleration doesn't change throughout the motion, okay? So that's what we are going to deal with in this chapter, okay? Of course, in real scenario, acceleration will be varying, okay? But in this case, for simplicity issue, we'll just look on the constant acceleration cases, okay? All right. So then let's take a look here. For average speed, okay, then it's defined as d over t, right? Distance traveled divided by time t. Now, sub AB means average speed, okay? In some cases, you see people with use the same notation as this guy use v with a bar on top. That means if you see that notation, that means average speed as well, okay? But you can do this as well. So notation doesn't really matter, okay? As long as you know what you are writing down, that's fine for you, okay? So from here, so the distance, or if you are indicating this is okay, so we are talking about one-dimensional motion here, okay? So then this could indicate also displacement, okay? As long as you have a positive and negative sign for displacement indicating its direction, okay, then this is displacement. So velocity average equals to displacement divided by t. Displacement is equal to final position minus initial position divided by t, okay? Then we'll be just looking at VAV equal to this guy. Okay, so forget about the middle expression here, d over t. Okay, so then in this case, if you multiply both sides by t, all right, then you get rid of t on the right hand side here. On the right hand side, you have x minus x naught. On the left, you have VAV times t, okay, which is this expression over here. All right. Let me see if online folks can see the whole screen or not. Okay. Okay. So now from here on, you can add x naught to both sides of the equation. Then you get rid of x naught on the right. Okay. So then on the left, you have VAVT plus x naught or x naught plus that equal to x. Okay. Which I'm going to switch the two sides. So then x equal to x naught plus VAT. Okay. Or v times v average times t. Okay, so x equal to x naught plus v times t. Okay, this is the average speed or average velocity. Okay, so this is the equation 2.28. All right, so this is basically a derived equation from definition of average velocity. Okay, for one-dimensional case. So your final, so this equation says your final position should be equal to your initial position plus average speed or average velocity times time t. Okay. So that's the first equation. The second equation here, so if this is constant oscillation, okay, you can see from the v versus t plot, then this curve should be a straight line. Okay, a straight line means it has just one slope, right? So that means the oscillation is constant because the slope will be equal to oscillation. If it's straight line, then it's a constant oscillation, all right? So for constant oscillation, your average velocity, okay, because it's a linear, so then it should be half of initial plus final, okay? So your average velocity should be 1/2 of initial plus final, okay? So this is equation 2.29 here for average velocity for a constant oscillation, one-dimensional motion. Now, similarly, you can do the same for the definition of the oscillation, okay? So average oscillation equal to change in velocity divided by t, which is final velocity minus initial velocity divided by t, okay? So you'll, again, multiply both sides by t, and then move the initial velocity to the other side of the equation, just like what we did for v equals to delta x over delta t in the previous slide, okay? The same operations, you'll arrive at this equation here, which tells you your final velocity is equal to initial velocity plus oscillation times t, okay? Pretty much the same as the, very similar to the previous one, okay? Equation, all right? Now, if you combine the two equations in the previous slide, the 2.29 and 2.35, all right, combine these two. So then substitute the V final in the bottom equation here with this expression, okay? Then you'll get this. So then V average is 1/2 of initial plus this final is equal to this guy, okay? V0 plus AT, all right? And along with the first, the equation we obtained in 2 slides ago, x naught equal to, or x equal to x naught plus VAVT, all right? Now, from here to here, you will be substituting VA average with this expression in it, okay? So then a couple of algebra there. Let me show you on the paper here so you can see how that is done, okay? Oops, let's do this way. No. All right, goes that way. So this is what we have on the PowerPoint slide. So you have x equals to x naught plus v sub av times t, right? And then this guy, VAV, is equal to 1/2 of V0 plus V0 plus AT. Okay. So then this is equal to x naught plus 1/2 of V0 plus V0. That gives me 2V0, okay, plus AT. So this is 2V0 times T. Okay. So then I need to distribute the T into the parentheses. Okay, there are two terms in the parentheses. Yeah, you guys wouldn't be able to see that. Sorry about that. Okay. All right. So x equal to x naught plus VAT, V average times T, V average equals that guy. So I'll be substituting VA average with this expression into this, okay? And then this is from here to V0 plus AT, and then I'll be distributing T into the first term and the second term there, okay? So then x naught or x equal to x naught plus 2 times 1/2, 1/2 times 2, that cancels out. So V0 times T, right? Plus, now 1/2, yeah, I also need to put 1/2 there. So 1/2 AT times T, right? So then this will be x0 plus V0T plus 1/2 AT to the second or squared, okay? So this is the what we have on the PowerPoint slide. Okay, so a couple steps of algebra there will get you to this one, okay? You guys, I encourage you guys to do the deviation as well, but it's not super critical that you have to know this, you don't have to know how to do this, okay? But I think you guys should be able to do it, okay? You will not be asked to derive this in an exam anyway, okay? So then this is what you have. So x now, x equal to final position. Yeah. So for you guys online, if sometimes I forget to share my screen, or if you there's an issue, say you couldn't hear me or whatever, just let me know, okay? Because there's a lot of stuff to do here. All right. Okay. All right. So I think we have played with several equations, and then all right, one more here, the last one here. So the last one here, again, we are playing with some of the equations we have either derived or learned so far. So for the last one here, it's actually based on 2.35 and 2.29. Okay, again, this is what we derived earlier. And then this is from, if this is a one-dimensional constant oscillation motion, then this is why you have average should be equal to 1/2 of initial plus final, okay? So from the 2.35 equation, you can rewrite to figure out your T in terms of V final and V initial and the oscillation, right? You'll need to move this guy to the left. So V minus V0 equals to AT, right? And then divide by both sides by A. So then V minus V0 divided by A should be equal to your T, okay? Just two simple steps here to get there. Now, combine these two, this guy and this guy. All right, I'll take both this guy and this guy, into the expression we derived earlier, the first expression. So this VAV then will be replaced by this expression. This T will be replaced by this expression, okay? And then again, a couple steps on algebra there, you'll get to this expression, okay? Final expression, okay? So for right now, you can just take a note on this one and this one, or pull up the PowerPoint slide on your end, and then I'm going to show you quickly how this is done on the paper, okay? So now I'll start with x equal to x naught plus 1/2 v0 plus v times t, which is v minus v0 over a, okay? So this is VAV and this is t. Just give me 1 second before I switch to my paper. Okay. All right. Okay. So we had x equal to x naught plus VAV times t, right? VAV is 1/2 of this, and then t is that guy, okay? So we are going to do this multiplied by this, okay? Now a is in the denominator, you can move a outside. So this is x naught plus 1/2a v0 plus v times v minus v0, okay? All right. Any questions you guys might have? All right. Now on this one, you can switch the two terms, okay? Then doesn't matter. So you can do v plus v0. So v plus v0 times v minus v0, okay? So if you remember, if you do a plus b multiplied by a minus b, that gives you a squared minus b squared, okay? From algebra, right? If not, you can, if you don't remember, you can do this again. You can do distribute a into this one and then that one, and then b into that and then into that. You'll figure out it's going to be that, okay? I'm not going to show that here. All right, so then according to that, this is equal to x0 plus 1/2a. Then you should have a squared, which is v squared minus v0 squared, okay? So let's multiply that, will give you this, okay? Now you can move x naught to the other side. So x minus x naught is equal to 1/2a v squared minus v0 squared. All right. You can multiply both sides by 2a to get rid of 2a on the right. Okay. So then 2a times x minus x naught is equal to v squared minus v0 squared. Oh, actually, I think I went too far away. We don't need that. Okay, that's what we need there. So we need it. We just need it. Right. So don't need this. We can check on this one. So I'm going to just retire it here. So 2a x minus x naught equal to v squared plus minus v0 squared. Okay. Okay. So this guy over here, I didn't need that one. Okay. So 2a x minus x0 is equal to v squared minus v0 squared. So then v squared, you'll move this guy to the other side equation. Add v0 squared to both sides, okay? So then v0 squared plus 2ax minus x naught is equal to v squared, okay? And then that's the expression we had, that's what we have on the PowerPoint slide, okay, the bottom of it, over here, okay? It's pretty much the same, you just switch, move, this was on the right-hand side on my paper, and then this is on the left-hand side, okay? But that's the same thing. All right. So I think I have derived a few equations here. I hope that doesn't scare you guys because you guys are not required to do the derivation. Okay. I just want to show you guys how those equations are derived. Okay. Um, so then these are the 5 equations we need for one-dimensional motions. Okay, so for any one-dimensional motions, these are all the equations you will need. Okay, so the first equation is x equal final position equal to initial position plus v. Okay, now it changes notation here with a bar means average velocity. Okay, so this is equivalent to v sub av times t, and then v average, this is v sub av again, just a different notation, is equal to 1/2 of initial plus final. Okay, final velocity is equal to initial velocity plus acceleration times t. Final position is equal to initial position plus initial velocity times t plus 1/2 at square. Okay, and then the last one here, v square equal to v0 square plus 2a x minus x0. Okay, acceleration times final position minus initial positions. Okay. Again, you guys don't have to derive these equations or memorizing them. Okay, they should be provided to you during the test. Okay, so with these 5 equations, you should be able to solve for all the problems in this chapter for one-dimensional constant oscillation motion. Okay, so final note how to solve a problem, a physics problem here particularly. Okay, so these are the steps you want to take. Okay, so first you want to read the problems carefully. Okay, just put it in that way. So you want to read the problem carefully to see what physical principles are involved. Okay, so to start with, in chapter 1, this is easy. This should be all in chapter 1 should be always one-dimensional motion, constant oscillation. Okay, so for right now it's easy, but as we get deeper into the semester, then we have so many chapter learns. Okay, then that's more critical. Okay, but for right now, it's simple. So determine what principle are involved. Okay, I think that's pretty much. And then and then you can list the equations that you learn under that particular physical principles, okay, or concept or topic. Now the second step is to figure out what are the knowns, okay, of the problem. Okay, so for the example we did earlier, we know like the oscillation was given, the time was given, final velocity is given. Okay, then we solve for the initial velocity. Okay. So sometimes for some problem, some information is not given directly, okay, but it will be inferred in the question. For example, if you release an object here somewhere, okay, then it says it starts from rest, okay, so that means the initial velocity is 0, right? So that's the information that is inferred or yeah, provided by the problem, but not directly stated. And then if you release it under the influence of gravitational oscillation, then that means your oscillation is also known, right? It's not directly given to you, but you should know that your oscillation is gravitational oscillation in that scenario. Okay, we'll get to details later on. Okay. Now, step 3, identify exactly what needs to be determined in the problem. Okay, so that's obviously very critical. If you get it wrong, then you'll get the wrong answer. Okay, at the end. Now, step 4, find an equation or several equations to solve the problem. So in this chapter, you will have those 5 equations listed in the previous slide. Okay, you can pick either 1 or 2, maybe sometimes 3 of them to solve the problem. Okay. Now, this doesn't get to you naturally. The only way to achieve this is after you have done so many practices. Okay, so remember, as I mentioned to you, you need to do your homework by yourself, not just get answers from somewhere else. Okay, so you need to practice on solving the problem. Okay, and then it helps you a lot if you can do more practice by solving the examples in the textbook or the ones we have done in the class by yourself before looking at the solution, okay? All right, and then step 5, all right? Now you have identified equation to be used, and then you'll be just plugging numbers on step 5, okay? Last step here, okay? It's also very important. Sometimes you can look at your answer and then say, okay, does it make sense? Okay, for example, if you're solving for a speed of like certain, say, a person, okay, running, if you get to say 90 miles per hour, then that doesn't really make any sense, okay? So then check again with your solutions or with your calculations to see what went wrong, okay? All right. Now, I don't think we have enough time for this practice, but if you guys can take a look or get started on this one before we meet on Friday, that will be very helpful to you guys, okay? So we will stop here for today for the lecture. Any questions you guys might have before we finish today's lecture? All right, again, so on the lab, let me make a final comment on that, okay? When you come in for the lab, okay? So Wednesday's lab, currently there are 17 of you guys in the class, okay? In the lab section. So we'll have a station set up for you guys. So that means the stations will be set at where there's a plexiglass dividers, okay? So that means 2 persons will work as one group on the station here, and then one station over there, one station here, and then here, there, okay? So pretty much 2 of you will work as one group, but because we have 17 students here, so the last group will have 3 persons work together. So probably either over there at the back row or there, okay? Because there are extra plexi dividers there, okay? Now bring your laptops here, right? And then if you don't have a Google account here, I encourage you to register one because we will be using Google account, okay? Another thing that I will give you guys face shield for the lab section because you'll be work closely to each other, okay? So we'll wear face masks as well as face shield, okay? To have extra protection, okay? All right. So I will see you guys here for the lab and then the rest of you guys on Friday.